Chapter 25 is all about electromagnetic radiation and electromagnetic induction. Now, electromagnetic radiation, we've already talked a little bit about. Electromagnetic radiation, light is an example of electromagnetic radiation, though there are other phenomena that we wouldn't quite call light that are also described as electromagnetic radiation. For example, in this picture right here, we see the exact same photo, but this photo has been taken in the visible spectrum, that is, electromagnetic radiation that you or I can see. We would typically call that light. This photo was taken in the ultraviolet part of the spectrum. So those are wavelengths of electromagnetic radiation that are shorter than the visible spectrum that you and I can see. There are also electromagnetic waves that have longer wavelengths, such as radio waves or infrared radiation. Electromagnetic induction, on the other hand, is a very interesting phenomenon that is actually all around us, but I'll bet you've never learned about it. So that's pretty cool. This idea of electromagnetic induction, which is where we're going to start our discussion, was first observed by Michael Faraday in the 1800s. Now, in the last chapter, we learned that moving charges, currents, can create a magnetic field. In this chapter, we're going to turn that relationship around, and we're going to say magnetic fields can create currents. But there has to be we have to have a set of specific conditions in order for that field to create a current. So one of the first experiments to observe this effect is shown on the slide. And what we see here is that we've got a battery or some other source of EMF right here. And this is an iron ring. And so when we close this switch, a current gets set up in this side. Notice we've got a coil of wire here. This is essentially a solenoid wrapped around this iron ring. Now, with the switch open, there is no current in the solenoid. With the switch closed, there is current in the solenoid. And so we see a magnetic field. It goes from 0 to something. In other words, we have a changing magnetic field. That changing magnetic field creates a changing magnetic field on this side of the ring, which creates a current in this loop. Now, it's important to recognize that we have no electrical connection here. Right? This is not a circuit like what we learned about in the last chapter. I guess that was a couple chapters ago. Because we can't actually have electrons flowing directly from here to here. So again, in this scenario, we have a changing magnetic field which induces a current. It induces a current, hence the word induction. We're going to come back to this idea in just a minute, but first we're going to talk about another way to induce a current, and that is by moving a conductor in a magnetic field. Let's start off with a quick example using some of what we learned about in the last chapter. So, a metal bar moves through a magnetic field. The induced charges on the bar are... Why don't you pause the video and see if you can't decide which of these selections is correct. Hint, you will want your right hand for this operation. Welcome back. Let's use our right hands. We have a velocity in this direction. We have a field that is out of the page. Therefore, we have a force in this direction on the positive charges. Remember that the right-hand rule only works for positive charges. So, our positive charges go this way, and our negative charges go that way. And indeed, that is what we observe. How about this one? Go ahead and pause the recording and see if you can't figure it out. Okay, in this case, we have a velocity that is towards the bottom of the page and a field that is towards the bottom of the page. So the angle between V and B is 0. And the sign of 0 is 0. Therefore, there is no force. The charges do not separate. PowerPoint agrees. I love it when that happens. So this is a separation of charge. And a separation of charge creates a potential difference. We learned that in capacitors, and we learned that in batteries. And we called batteries an EMF. We called the voltage produced by batteries an EMF because it used chemistry to separate the charges. Now in this case, we're separating charges, but we're not using chemistry, we're using motion in a magnetic field. And so we call it motional EMF. Emotional EMF is a topic for a whole nother class, so we won't go into that. Here we see this slide here, which gives us a diagram of what we just looked at, but with a nicer drawing than what I was able to produce on my mini blackboard. So notice here that with our right hands, we have the velocity in this direction. We have a field that is into the page. That gives us a force to the top of the page. Ooh. Okay. Let's see. Indeed, this lovely picture confirms what I just figured out with my right-hand rule. Looking at this, we've got a moving bar in a magnetic field, a moving conductor in a magnetic field, which causes a separation of charges. Well, when does the separation of charge stop? These positives are attracted to these negatives. And so this separation will continue until the electric force on those charges is exactly balanced by the magnetic force. And when that happens, you can see we do a little bit of algebra here. These Q's can cancel. And we get a relationship between the electric field and the magnetic field. This is an interesting result, and one that we'll see actually shows up again when we talk about electromagnetic radiation. It'll show up in a slightly different form, though. So now we have an equation for motional EMF. Motional EMF is equal to velocity times length times the magnetic field. Okay, let's do an example. Okay, we have a Boeing 747 aircraft with a wingspan of 65 meters. It's cruising at 260 meters per second over northern Canada, where the magnetic field of the Earth is directed straight down. What is the potential difference between the tips of the wings? Well, we'll want to use the equation for the motional EMF, since we have a conductor moving in a magnetic field. So that looks like this. EMF equals B times L times V. Well, really, at this point, we can just plug in. Our B is 5 times 10 to the negative 5th Teslas. Our length is 65 meters. And our velocity is 260 meters per second. So now we run our calculator and we get 0.845. And what's our units for EMF? Well, volts, of course. And so that is our answer. Woohoo!